Hello, in this video we're going to look at some volumes of rotation that can be created using either cylindrical shells or using washers. So let's look at these examples. So you can read the example. We have a region bounded by the x-axis, x equals 4, or y equals the square root of x, and it's rotated about the y-axis. So you can see the illustrations here of this. There's a two-dimensional picture showing what's happening. And let's see, let me move this over here, get out of the way. You can see if we look at the first picture, this is our 2D version of it. And so we have our region on the right that is going to be reflected over the y-axis and give us the region on the left. But if we actually were to rotate the single rectangle, it's going to give us a cylinder if it's rotated this way. So we're going to start looking at this in terms of cylindrical shells. And hopefully you've memorized the formula for cylindrical shells, that the volume would be 2 pi r times the height times delta x if it's a vertically aligned shell, because this is one dimension is that it's delta x thick. The 2 pi r comes from going all of the way around the circumference, and the height of the shell is the third dimension. So the product of those three dimensions gives you the volume. When you fill the region with rectangles and rotate them all, this is the total volume picture right here. And our computer calculated that the answer would be about 80.49 cubic units. So let's go ahead and set this up and solve the problem for this example using cylindrical shells, and then we'll come back and look at it using washers instead. So if we were to look at this particular shape, we would start by writing our volume element. Delta V is equal to 2 pi r h times delta x. So we'll be able to convert this into a volume integral if I can write out what r is and what h is. Now h is the easier of the two. So to get the height, if I just look in this picture, the height is going to extend vertically like that for any given rectangle. No matter where these rectangles are, I'll draw another one over there and another one over here. If I fill the region with vertical rectangles, they're all going to have, to find the height, we're going to do top minus bottom. All of them have a height which is given by the curve, which is the square root of x, minus the bottom, which is 0. So we can say that the height is simply the square root of x. What is the r value? Okay, the r value, to get that, it's always a good idea to draw a radial line from the axis of rotation. So notice I started right on the y-axis because that's where the axis of rotation is, and I went all the way out to where the cylinder is. So in this case, the cylinders, if I look at all three of the rectangles that would be generating cylinders, they all extend out to an x value. So the r, the radius of our cylinders, will just be the x value of where the rectangle is. So I can just put that all together and get that delta V is equal to 2 pi, instead of r, I'll have x. Instead of h, I'll have the square root of x times delta x. I can simplify that and say delta V is equal to 2 pi. Since we're about to do some calculus, we'll call this x to the 3/2 delta x. And then I can turn that into an integral. And I can say that the volume of this should be the integral of, I'll put the 2 pi out front, and then I'll have x to the 3/2, and the delta x becomes dx. And I'm going to integrate from x values starting at 0, and I'm going to go all the way up to x values of 4. Okay, so this is the volume integral. This one would be very easy to calculate because it's simple power. So I could easily calculate it and determine what the volume is. But likewise, I could take that same region and I could use washers. Now the diagram has a vertical rectangle in there. If I'm going to use washers, I would actually have to create rectangles that are horizontal. So you may want to, if you wanted to, you could have washers made out of these, and as they spin around, they're going to correspond to rectangles over here. I'll just draw the middle one over there. So you can see if they were to spin around, they would leave a hole in the middle. And then they would have a large disc on the outside. So I got a little bit crowded, so I'm going to remove those last couple of lines. But you can see that that would form a washer because of the gap between the rectangles as they spin around. So if I want to use the washer method, I should start with a formula for a washer, which is delta V equals pi times R outer squared minus R inner squared times, in this case, it's a delta Y. Now that's important. Since it's a delta Y, everything needs to be written in terms of Y. So I'll write down below what R out is and what R in is. And let's come up with equations for those, okay? The outer one is going to be the easier thing because you can see all of the rectangles that I would draw that are horizontal all line up with the red line that I just drew in. So where is that red line? That's at x equals 4. So the outer value is always 4. The inner value is going to be variable. So these are lining up with the curve on the inside. And the curve was y equals the square root of x. But because we said that it's a delta y here, we need to rewrite this so that we can have a relationship between x and y that's in terms of y. So it'd be pretty easy to rewrite this one as x equals y squared. So what is the inner radius? The inner radius will be y squared. Now, a good quick check, let me just do this in green, is if I have make a little y table versus what our inner is. When y is down at 0, that's down at the bottom here, we're expecting to have a 0 for the inner radius, which since the inner radius is equal to y squared, that will in fact be 0. But by the time y gets up to 2, y squared will be 4. So you can see up at the top, the inner radius is the entire radius, which is 4. So that worked out nicely. So this table is a good quick check on whether you wrote it correctly. So now I can go in and I can fill in my volume integral. And that will be that delta V is equal to pi. I'm sorry, not the volume integral, but the volume element. And I'm going to have the outer radius squared first. So I'll just write that that's 16 minus, and then the inner radius squared. Now be careful. The inner radius is y squared, so when we square it, that is y to the 4th times delta y. I can turn this into a volume integral. Slide up a little bit. Let's put the pi out in front. We're going to take the integral of 16 minus y to the 4th dy. And we're going to start at y values. Notice it's y is going to start at 0 and go from 0 up to 2. So it's not going to 4 anymore. Y is only going to 2. So this integral would also give me the volume of the shape. Now you can see this one doesn't have fractional power, so this might actually be the easier one to integrate in this case. So it looks like if I write this as washers, it might in fact be easier to do, but not that much easier. Either method is pretty good. Now, if I look at the top region, let me scroll on down. Oh, here we go. Okay. If instead of doing the problem I had just done, if I look at the region, just to line up, there we go, bounded by the y-axis, y equals 2 and y equals the square root of x, and we rotate about the y-axis. Instead of having the region below the curve y equals the square root of x, we're looking at the region above it. So when that rotates around, instead of making sort of the stadium shape that it did before, it looks like we sort of have a whole volume that's sort of a funnel shape. You can see we still have a cylindrical shell, or I'm sorry, yes, we have a cylindrical shell that we could use if we wish to, and that corresponds to the 2D image that we have over here. So this is a single element. That will be a shell, and we can go about doing the calculation for that. Okay, so if we're going to use cylindrical shells, it's best to work off of the 2D picture. So let's write what the volume element would be. It would be delta V equals 2 pi r h delta x. So that equals 2 pi times, oh, I am sorry, we need to write out what r and h are. So let me simply write those underneath. R equals, H equals, and then let's fill these out. Now this will be slightly more complicated this time. The radius ends up being the same because if you look at, if you draw in a radial line to where the rectangle that's being rotated would be, it's still at a value of x. So we can still write that the radius is x. Now the height is going to be this height right here. So once again, we want to do top minus bottom. So if we look at where the top is always at a height of 2. And the bottom is bumping against the curve. And since we're working with delta x, we will want to write that as the square root of x. So then we can fill that in. Delta V is equal to 2 pi. Instead of r, we can write x. Instead of h, we can write the quantity 2 minus the square root of x, delta x. We can turn that into a volume integral. Let's put the 2 pi in front, and we will be integrating the integrand x times the quantity 2 minus the square root of x dx from x values of 0 out to x values of 4. Now, hopefully you would see that if you were going to do this by hand, you would want to distribute, and you would have a 2x and an x to the 3/2 power in the integrand once you distributed it, and then you would be able to do this by hand. We're not going to bother doing the calculation right now, but that would be relatively easy to do using cylindrical shells. I could do the same thing with washers. We'll ignore that vertical rectangle, and you would have to have rectangles that look like this. Let me just put 2 of them in. Okay, so you can see at the top, the reflection would actually form a disc, but actually the reflections will be discs everywhere. So while we're calling this the washer method, it's a washer without a middle. So it will become a disc because the inner radius will always be 0. So the washer method and the disc method just coincide when there is no hole in the middle. So we could write a volume element, delta V is equal to pi, we just have an outer radius squared times delta x. So I'm sorry, there's a mistake there. That is not delta x thick, that is delta y thick. Okay, these are horizontally aligned, so the thickness in the vertical direction is the delta y. These are both very skinny, so they are delta y in thickness. So underneath, we just have to write what the r value is. Okay, the r value for those green rectangles are going to go from here out to the curve. So you can see that no matter what, the outer radius is going to be on the curve itself. And the curve, we already talked about this, you could call it y equals the square root of x, but you need to write it in terms of y since we have a delta y, so you better say that x equals y squared. So the outer radius is y squared. So when we look at this, delta v is equal to pi times r squared. Now be careful, r is y squared, so that will be y to the fourth times delta y. So we could turn that into a volume integral and put the pi in front, and we could integrate y to the fourth with respect to y. And we would start at y equals 0 and go up to y equals 2. You can see this would be actually quite easy to evaluate. So in this case, it's probably easier using the disk method than it would be using the shell method to get an answer. But neither method is going to be that difficult.